The International Space Station has been in orbit around the Earth for 25 years, demonstrates mankind's extraordinary achievements in space exploration. Today, NASA has invested more than $400 million start developing a new generation of International Space Station 2. Zero items. But our exploration ambitions should not be limited to Earth orbit. In order to go deep into space, we need to develop completely new technologies, such as habitable mini-planets or other giant structures, maybe even deploying a megastructure on a hemisphere near the Sun, to control the future of our solar system. Imagine if we could build a giant generator, extracting endless energy from a tamed black hole. What a spectacular achievement this would be! These ambitious space structure projects not only face huge technical challenges, and provides mankind with unprecedented opportunities for exploration. In this video, I explore whether building a space giant like the Death Star is really worth it, why reshaping the Earth itself might not be a good idea. NASA is working with private companies NanoRex and Virgin Space Cooperation, committed to this ambitious goal. They plan to launch the private Stala space station into orbit in 2027. This will not only be a scientific research laboratory, it will also become a center for space tourism. This space station will be equipped with a 340 cubic meter air bottom module, although the internal volume of this ISS is 3 times smaller. But it solves many of the problems facing the International Space Station. Starlab's breathable bottom module adopts an inflatable design, constructed from multiple layers of patented material. These materials help protect the space station from cosmic radiation damage and gas leaks. It is worth noting that this is a private project. This is different from the government-led International Space Station. However, the International Space Station now faces the challenge of technical errors. It has technical support from the United States, Japan, European countries, Canada, and Russia, etc. Each participating space agency is responsible for the feasibility of its own module, perform regular inspections and maintenance to extend module life. NASA, JSC, and CSAC plan to operate its module until 2028. The Russian Cosmos module is responsible for keeping the International Space Station in orbit, prevent it from falling to Earth. But by 2024, the International Space Station may need to be decommissioned early, despite the smaller size of Starlab. But it won't solve one of the main problems facing the International Space Station: effects of long-term exposure to zero gravity on the human body. Weightlessness not only brings inconvenience to astronauts, it also increases health risks. Long-term weightlessness can cause astronauts to quickly lose awareness. Decreased valley density increases the risk of valley folding. Space agencies around the world are studying the short and long-term effects of zero gravity. But so far, the results of these studies are not promising. If we could build a space station with artificial gravity, then long-term space missions will become possible. We will be able to send astronauts to any corner of the solar system. However, creating artificial gravity is not a one-and-done matter. A huge challenge facing humanity is how to build a planet-like space station, or even a mini-planet. To achieve this goal, we have 2 possible methods. The first is to simulate natural processes, the natural formation process from around Asteroid to a mini replica of Earth. The second is to directly build a planet-shaped space station, like our own version of the Death Star. Take the Death Star as an example. Assuming its diameter is about 140 kilometers, if made of steel, its mass will reach an astonishing 100 billion tons. This time, although this number is only 1/10,000,000th of the mass of the Earth, but building such a massive structure remains a huge technical and resource challenge. Give an example. It took 3 years to build Dubai's million-ton Burj Khalifa. 10,000 workers were employed. So build a giant structure like the Death Star, maybe more complex and time-consuming. As noted by aerospace engineer Mark Hummel in the Journal of the British Interplanetary Society, to create a mature star, we need the equivalent of 11 Earth masses. If we compressed 700 gold tons of material into a sphere the size of the Moon, we will be able to experience Earth-like gravity on it. But how to achieve this compression is a huge challenge. One possible solution is to harness solar energy by deploying fusion reactors near the sun. We may be able to generate the heavy elements we need to build our planet. Such a reactor would collect hydrogen from the sun's surface and use it to produce heavy elements like how and thin. After these elements are heated to 5,100 degrees Celsius, will be launched to specific locations in the solar system by colliding and combining with each other, eventually forming the core of the planet. When these elements are cooled to 1,600 degrees Celsius, they can be covered by a silicon layer, thus forming a structure similar to the Earth's crust. However, to create enough silicon and other materials to build a ground bridge for artificial planets requires a lot of resources. For example, the amount of steel required to build the Death Star reached 100 billion tons. The current annual steel production on Earth is only 2 billion tons. To avoid taking up to 800,000 years to mine these resources, we have to find other sources of lumped metals. For example, heavy objects in the asteroid belt. For example, one of the largest objects in the asteroid belt. He owns nickel alloy pestles worth up to 10,000 kilograms of US dollars. These resources should be enough to build and deploy a Death Star. In addition, celestial bodies such as Loki and asteroids can become sources of materials for artificial planetary ground bridges. But in order to exploit these resources, we need new technologies and equipment suitable for working in low-gravity environments. Although these efforts may seem daunting, but building artificial planets could potentially solve the major problems facing modern space warfare, such as lack of gravity. For structures like the Death Star, the construction had to be very different from the Death Star in the movie. Engineer at NASA's Jet Propulsion Laboratory, Adam Stelzner thinks, to create Earth-like gravity inside the space station. This can be achieved by placing rockets in the orbit of a sphere. These rockets will cause the entire structure to rotate on its axis. Gravity is generated internally with the help of centrifugal force in addition. Since there is no friction in space, rockets don't need to work continuously. Such a space station internal structure will resemble an onion where the layers will be stacked. Technically speaking, the layers near the center of the sphere place the energy's gravity well below the outer shell. However, a major drawback of this structure is the instability. Stelzner believes that in order to maintain stability, for example, the crew must constantly monitor the space station's exact orbital parameters and make adjustments. In exploring the concept of artificial planets, building a complex for scientific research seems to be a relatively easy task, because in such a structure, stability and gravity issues can be effectively addressed. However, a major challenge is time. Even if we build a fusion reactor near the sun and found enough to return to construct the Earth, building a planet from scratch would likely take at least 10,000 years. This is clearly beyond the realm of science fiction, entering a long-awaited reality. At this point, we might as well consider some of the crazier scenarios conceived by scientists and science fiction writers. Megastructure. American architect Buckminster Fuller proposed the KEO-9 project in the mid-1950s. This is a sphere 1 kilometer in diameter, floating in the atmosphere like a hot air balloon. Fuller calculated that in order to make this structure float, the air inside the sphere only needs to be 1 degree Celsius warmer than the outside. Such a structure could accommodate hundreds of residents. They can enjoy the changing scenery through the windows. However, applying such a structure to the Yunji civilian project on Venus is full of challenges. Venus' acidic atmosphere and strong winds make this idea almost a one-way ticket to hell. On Earth, such structures may meet a similar fate to the airships of the 1970s. Physicist Gerald O'Neill proposes a different idea, like an O'Neill cylinder. Although this structure is only 500 meters in diameter, but it can accommodate 10,000 residents. By rotating at a speed of 2 revolutions per minute, cylinder can generate artificial gravity inside it. The environment in which residents live can include forests, river, and farm. To build a perfect Earth-centered world, however, even if such a structure sounds more practical than terraforming Mars, they also face serious challenges, such as cosmic rays. Due to the lack of protection from the Earth's atmosphere, residents of the original habitat could be exposed to lethal doses of radiation. Also, the impact of a meteor would be enough to turn this megastructure into a giant tomb. On a larger scale, some ideas don't even consider security issues. For example, Swiss architect Christian Valvagel's Globus Cassis project proposal will almost the ball flipped over, smear all its contents onto a giant sphere. This mega project covers everything from building a space elevator to transporting a ground bridge over the Diamond River into orbit. In this structure, gravity will shift from the core to the rotating outer shell, just like the original O'Neill cylinder. While such a project is theoretically possible, but in fact, we need to face huge technical challenges. Imagine that a 1,000-kilometer-long tower crane falls to the ground, could destroy an entire city. However, we can't help but imagine that in Globus. What a day in the life of a Cassis construction site is like. However, even this Hongbei project, Uten, the huge habitable disc box designed by Alderson, is a relatively wild and dangerous box-shaped building. In the mid-1970s, proposing such an idea was almost like making a flat Earth joke. Because the diameter of Alderson's disk exceeds 240 million kilometers, extending beyond the orbit of Mars, its track thickness reaches 5,000 kilometers. In fact, the migration area of the disk is limited to a narrow strip in the middle. But according to Alderson's design, this area will be 50 million times the size of Earth, enough to accommodate trillions of people. But there are always some details that need to be paid attention to. For example, since the Sun is always on the same side, the Alderson disk will always be under an eternal gaze. It would be very difficult to walk on such a flat surface, because people are always pulled to one side. We may need to ask goats to teach us how to climb in this environment. However, these changes may not last long. Due to gravity, any oddly shaped object will eventually turn into a regular sphere. Alderson disk will be more massive than our Sun. These objects may eventually merge into a new bright star. Its inhabitants will also become its fuel. In our solar system, the Sun revolves around the Milky Way, and it's like we're in a racing car without a steering wheel. Soviet engineering lost. Onadorf proposed a method of guiding the solar system in the late 1980s. A curved mirror with a diameter of 300 million kilometers. That's the stellar engine. According to calculation, this engine may be around in 200 million years. Move our solar system 80 light-years away. This will be the greatest engineering triumph in human history. American physicist Matt Kaplan is also interested in this idea. It recently developed a smaller device, only a few kilometers big. It collects Chingha-C from the Sun and burn them in thermonuclear reactors. Kaplan thrusters accelerate the solar system to more than 30 kilometers per second and covers 50 light-years in 1 million years. But this thruster also has its weaknesses, such as electromagnetic anchor, even a glitch. It may also cause the device to crash into the Sun, cause massive solar wobbles, burn all electronic devices on Earth. In front of these amazing ideas, the most stable megastructure we can build, maybe it's the actual pyramid. In this imaginative vision of space exploration, we might even consider using Kaplan thrusters as a means of transportation. Head to the black hole to start a new construction. In such an extreme environment, build a megastructure, especially using black holes as energy sources. Sounds crazy and dangerous. Physicist Roger Penrose proposes a way to use black holes as energy sources. That is, Pangloss process. The process involves a spinning black hole. Its event world is surrounded by an area called Augsfell. This region distorts space-time around the black hole, but in theory you can leave. Penrose suggested launching a bipolar rocket into the area. Part of the advancement will fall into the event world. The other part is accelerated by the energy generated by the black hole's rotation. To build a generator, we need to build 2 sites near the black hole. Each site is approximately 10 kilometers long. One station emits light, another station captures the light. Produce powerful laser. This method could allow us to extract energy from black holes. support our colonial development. However, in order to avoid energy leakage, we may need to use the method proposed by Skotov. That is, 2 curved mirrors are used to surround a quarter of the black hole. The light in this light cage will continue to accelerate, and then accelerate it again from specular reflection. But this process sounds simple only in theory. In actual operation, unpredictable quantum effects near black holes could turn our giant generator into a giant bomb. If we cannot control the chain reaction of photon acceleration, this structure may explode with the force of a supernova and destroy everything. Eventually, if we move to the idea of a safer megastructure, then we could consider building a giant inflatable colony on the moon. This structure can be up to 11,000 kilometers long, use durable materials and powerful pumps to maintain structure. Even in the event of impact or leakage, repairs can be done using simple repair methods such as tape. Such a colony could become a relatively harmless and practical environment for space habitation. Although these ideas sound challenging, but they demonstrate mankind's infinite imagination for space exploration and habitation. From theory to practice, we still need to overcome many technical difficulties. But that's what drives us forward.